Hey, today we're going to talk about limits at infinity and beyond. That's a joke. There's probably something wrong if you have to say that it was a joke, but anyway, let's take a look at this graph of the function y equals 1 over x. And you can see what happens as the x values get larger and larger as they go towards infinity. The function values, the y values, get closer and closer and closer to 0. Same thing, as the x values get larger and larger in the negative direction, the y values get closer and closer and closer to 0. These are horizontal asymptotes. This is the whole idea behind limits at infinity. And here's our pseudo definition. We say that the limit as x approaches infinity of some function f is equal to some number L if and only if, that's what that IFF stands for. It's an abbreviation for if and only if. So if and only if the values of the function f get arbitrarily close to L as x gets sufficiently large. So this is not the precise definition, but there is one where the arbitrarily close to L is within epsilon, and there's some similar concept for what it means for x to get sufficiently large. So that in particular, in this case, we can see from the graph, or just by thinking about it, that the limit as x approaches infinity of the function 1 over x is equal to 0. The just by thinking about it part, pick your favorite really large number x. That's the idea of x approaching infinity. A trillion. Well, 1 over a trillion. 1/1 trillionth. That's a very tiny number, very close to 0. You want to get closer to 0, pick a bigger number for x. Similarly, for this particular situation, the limit as x approaches negative infinity of 1 over x, also equal to 0. These are what we call horizontal asymptotes, and we'll say that a function has a horizontal asymptote if the limit as x approaches infinity or negative infinity is equal to some real number. Let's take a quick look at an example. This is a graph of the function y equals the arctangent of x, where f of x is the arctangent of x, the inverse tangent. The tangent function is a horrible function, undefined in infinitely many places, but its inverse, the arctangent, is a beautiful function defined for all real numbers. And you can see that as x gets larger and larger and larger, the function values are approaching pi over 2. So the limit as x approaches infinity of the arctangent of x, pi over 2. Similarly, if you look at what happens as x approaches negative infinity, it's pretty clear that the function values are approaching negative pi over 2, so the limit as x approaches negative infinity of the arctangent of x is equal to negative pi over 2. It's worth noting that the limit laws that we've established all hold for limits at infinity. So for example, the limit as x approaches infinity of the sum of two functions is the sum of the two limits, provided those limits exist. What is the limit as x approaches infinity of 1 over x cubed? Well, first of all, you can think about it intuitively. Think of your favorite large number, a trillion. A trillion cubed is a giant number. 1 over a trillion cubed, a very, very tiny, tiny number. You take your pi, you divide it into a trillion cubed pieces. You can have one of them. You have a very, very, very small piece of pi. How much? Almost nothing. This limit is equal to 0. Another way to do it is to apply the limit laws. And we have a limit law that says the limit of some function cubed is the limit of the original function, all cubed. In other words, you can cube the limit. And we've already computed the limit as x approaches infinity of 1 over x. It's equal to 0. And so this is equal to 0 cubed, which is just 0. And by the same reasoning, for any natural number n, where the natural numbers are the numbers 1, 2, 3, 4, etc., not 0, not negative numbers, not fractions, but just the counting numbers, or the natural numbers. For any natural number n, the limit as x approaches infinity or negative infinity of 1 over x to the n is equal to 0 by the limit laws. Let's consider this limit. The limit as x approaches infinity of 2x to the 4th plus x cubed plus 1 over x to the 4th plus x squared plus x plus 1. One thing we could try is applying the limit laws, and there's a limit law for quotients that says that the limit of the quotient is the limit of the numerator divided by the limit of the denominator. but the limit of the numerator is infinity. As x goes to infinity, so does 2x to the fourth plus x cubed plus 1. And the limit of the denominator also infinity. And so in that case, neither of those two limits exist, and so the limit laws don't apply. And so we need some different technique. And the different technique is algebraic. And if you're working with an algebraic expression, there are always two things that you can do to it that don't change the expression. You can add 0, which is sometimes helpful, but will not be what we do in this case. Or you can multiply by 1. Multiplying by 1 doesn't change the number, and it turns out that that does us a world of good in this case. In particular, there are lots of different ways to write 1. And one of them is as 1 over x to the fourth divided by 1 over x to the fourth. So I am essentially dividing the numerator and the denominator by x to the fourth. Let's see what happens algebraically. After you distribute the 1 over x to the fourth in the numerator and the denominator, you get that the original limit is equal to the limit as x approaches infinity of, well, 2x to the fourth times 1 over x to the fourth is just 2. The x to the fourths cancel. X cubed times 1 over x to the fourth is 1 over x. And 1 times 1 over x to the fourth is 1 over x to the fourth. In the denominator, x to the fourth times 1 over x to the fourth is 1. X squared times 1 over x to the fourth is 1 over x squared. X times 1 over x to the fourth is 1 over x cubed, and 1 times 1 over x to the fourth is just 1 over x to the fourth. A couple of things to say about this. First of all, you absolutely need this limit here. It is not at all true without that limit. The limit as x approaches infinity of the first expression is certainly not equal to this expression right here. It's equal to the limit as x approaches infinity of that expression. You cannot drop the limit. It will no longer be an equality, a valid equality. And the second point is, you really do have to do the algebra carefully. In other words, we really are distributing 2x to the fourth plus x cubed plus 1 all times 1 over x to the fourth in the numerator and something similar in the denominator. And so you have to be able to do the computation, what is x cubed times 1 over x to the fourth? And you have to be able to do that with great confidence and accuracy. That's x cubed over x to the fourth. And if you like, that's x cubed times x cubed, because x times x cubed is x to the fourth, and the x cubed cancel, and that's just 1 over x, and that's where we got this 1 over x right here. And so make sure that you can do all of those algebraic maneuvers with great confidence and competence, and if you can't, practice them so that you can, because they're going to be absolutely required in order to be able to do these problems. Okay, we haven't finished the problem yet, but we have come very close to finishing the problem because now we can apply the limit laws. The limit laws say that this is the limit of the numerator divided by the limit of the denominator, like so. And then the limit laws further say that the limit of 2 plus 1 over x plus 1 over x to the fourth is the limit as x approaches infinity of 2, plus the limit as x approaches infinity of 1 over x, etc., etc. In other words, you can break the limit of the sum into the sum of the limits in both the numerator and the denominator. And the beautiful thing here is we know each and every one of these limits. The limit as x approaches infinity of 2 is just 2. The limit as x approaches infinity of 1 over x is 0. The limit as x approaches infinity of 1 over x to the fourth is 0. The limit as x approaches infinity of 1 is just 1. And all those other limits are 0 because they're the limit as x approaches infinity of 1 over x to some natural number power. And so in the end, you just get 2 over 1. In other words, you get 2. And so this limit is equal to 2. And the first thing you say to yourself is self. Wow, that was pretty cool. And then the second thing you say to yourself is self. That's a lot of work to show. A lot of things I have to write down in order to get to this answer of 2. And I wonder how much of it he really wants to see on a quiz or an exam. Excellent question. I definitely want to see this. In other words, I want to see that you understand that you should be multiplying the numerator and denominator by 1 over x to the 4th, or dividing them both by x to the 4th, multiplying by 1 in some clever way like this. And then I definitely want to see this. I want to see that you are able to do the algebra and come up with some accurate result of what you get when you do that multiplication. And then I don't need to see that you can write limit of the numerator over limit of the denominator, and I don't need to see that you can write limit of the first term plus limit of the second term, etc., etc., etc. I think that for these terms in here, you can probably just do that in your head and see what's going on. But bizarre as it sounds, I would like to see that. Even though the 2 plus 0 plus 0 looks weird and is strange, you know, it comes from this step up here, and it shows me that you actually took the limit of 1 over x and 1 over x to the 4th to get the 0 here and the 0 here. And so I want to see that you've computed each of those limits. And so this strange looking step here is important to show that you know what you're doing. And then, of course, I want to see the final answer simplified, that is equal to 2. And you say to yourself, how did he decide to multiply by 1 over x to the 4th over 1 over x to the 4th? Well, here it is written out very carefully. You always multiply by 1 over x to the n over 1 over x to the n, where the n is the highest power of x in the denominator. Now, in this case, the highest power of x in the numerator and the denominator were both the same. That won't always be the case. Always choose the highest power of x in the denominator. We'll try a few examples, and hopefully that will help you see why. Okay, here we have 3 limits to compute. Take a few minutes, give them each a try, pause the video, and then we will breeze through them very quickly together when you are ready. So give it a try. Start the video back up when you're done. All right, taking a look at the first one, we multiply numerator and denominator by 1 over x cubed. After you distribute, you get 1 minus 1 over x plus 2 over x cubed in the numerator, 5 plus 1 over x squared minus 7 over x cubed in the denominator. And then when you take the limits, you get the limit as x approaches infinity of 1 is 1, limit as x approaches infinity of 5 is 5, and all those other limits are 0, and so you get 1/5. And you say to yourself, how did I know that the limit as x approaches infinity of 2 over x cubed is equal to 0? Well, good question. If you break it up algebraically, 2 over x cubed is just 2 times 1 over x cubed. And then we can use the limit laws to pull the constant 2 outside of the limit. And we already know what the limit as x approaches infinity of 1 over x cubed is. It's 0. So this is 2 times 0, or 0. Same thing for the limit as x approaches infinity of 7 over x cubed. Also 0 for the same reason. For this next one, the highest power of x in the denominator is x cubed. And so we multiply numerator and denominator by 1 over x cubed. You do that carefully, and you see that you get, after you distribute, the limit as x approaches infinity of 1 over x plus 3 over x squared plus 4 over x cubed, all over 1 plus 1 over x minus 7 over x cubed. And then when you take the limits of all those terms in the numerator are 0, and in the denominator, you get a 1 and a couple of terms that are 0. That gives you 0 over 1, and 0 over 1 is 0. And so this limit is equal to 0. This last one is not tricky, but ever so slightly different. The highest power of x in the denominator is 2, and so you multiply by 1 over x squared over 1 over x squared. And after you simplify, you get this expression that we see here, x plus 4 minus 7 over x squared divided by 1 minus 7 over x squared. Now, as x goes to infinity, this x term right here is going to infinity, of course. The 4 stays a 4, and this term is going to 0, and this term is going to 0. And so what we essentially have is infinity plus 4 minus 0 over 1 minus 0. Well, 1 minus 0 is 0. 4 minus 0 is 4. we essentially have infinity plus 4, which is infinity over 1. We have infinity over 1 or infinity. That's just the reasoning it out, thinking about it stage or phase. That's the way I want you to think about it. What I don't want you to do is write something like this, right? That's equal to infinity plus 4 minus 0 over 1 minus 0, which is equal to infinity. You can't do that. You can't do arithmetic with infinity. Infinity is not a number. Infinity plus 4 is conceptually infinity, but not arithmetically infinity. It doesn't work that way. And so don't do that. And so what can you do? Well, at this step, you can reason about it the way we talked about it a moment ago. As x goes to infinity, the x in the numerator is going to infinity. Everything else is a constant or going to 0. This limit is equal to infinity. So at this point, you are ready to say equal to infinity, and I'm perfectly happy with that answer. In fact, that's what I would like you to do. Okay, those are the basics of limits at infinity. I want to give you a couple of more quick ones just to make sure that you are prepared for any tricks that might show up on the homework. But first, I'd sort of like to give you the idea of what's going on here so that you can stare at one of these and immediately know the answer, which will not help you at all in terms of what you have to show to get credit for it on a quiz or an exam, but at least you'll know that you got the right answer after you do the work. So sort of this is a way to check your work and to understand what's going on, but does not get you out of showing this work. In other words, what I'm about to tell you, I don't want it spit back at me on a quiz or exam. This logic, this reasoning will not help you get any credit. So, all right, here we go. Let's look at this first one. The limit as x approaches infinity of x cubed minus x squared plus 2 all over 5x cubed plus x minus 7. Well, as x approaches infinity, imagine your favorite really, really large number, a trillion, for example. Well, you've got it in the numerator, you've got a trillion cubed. That's a giant number. And then you're subtracting a trillion squared. Well, you might think a trillion squared is also a giant number, and in some senses it is. But a trillion cubed is a trillion times larger than a trillion squared. A trillion times larger, astronomically larger than a trillion squared. And so the trillion squared hardly matters. And if that's not big enough for you, then a trillion wasn't a big enough number to start with. Take the number of atoms in the universe, whatever that is, and cube it, and subtract the number of atoms in the universe squared. Well, the number of atoms in the universe squared, tiny, tiny little number compared to the number of atoms in the universe cubed. Think of it this way if you didn't like that. Take a trillion squared, now add 2. Did that really change it much? No. Adding 2 to a trillion squared, you wouldn't even notice the difference on your calculator. Same idea. A trillion cubed, far larger than a trillion squared, and so it wins. The idea, the highest power of x in the numerator wins. It starts to become the dominant force in the numerator, the larger that x gets. When x is 10, it doesn't matter. 10 cubed minus 10 squared, the 10 squared matters. But when x is 10 trillion, then the 10 trillion squared doesn't matter compared to the 10 trillion cubed. So as x gets really, really large, and as you go to infinity, you can get as large as you like, the highest power in the numerator wins. It dominates what's happening in the numerator, and the same thing in the denominator. The highest power in the denominator wins. And so the larger that x gets, the closer this expression gets to x cubed over 5x cubed. And x cubed over 5x cubed is a fifth. And you'll notice that's what we got as our answer, a fifth. That's what's going on there. Same kind of thing is happening in the next one. As x gets really large, the highest power in the numerator and the highest power in the denominator are the ones that are dominating what's going on. And so the larger x gets, the more this starts to behave like x squared over x cubed, which is equal to 1 over x when you simplify it. And we know that as x goes to infinity, 1 over x goes to 0, and that's why we got 0 here. And then finally for this one, as x gets larger and larger, the largest powers of x in the numerator and the denominator dominate, And so we get something that starts to behave more and more like x cubed over x squared. And x cubed over x squared is x. And as x goes to infinity, x goes to infinity. And so that tells you how to just stare at these and immediately see the answer. Doesn't help you at all in terms of the work that you have to show to prove that those are the answers, but at least it gives you some intuitive idea of what's going on, and you can easily check your work. Okay, I just want to show you these last two so that you're ready for anything that you see on your homework. Take a moment, pause the video, give these a try, and then come back and I'll show you where the tricks are, if there are any tricks. Maybe there will be. Okay, for this first one, there's not really any trick. As x goes to infinity, well, it's sort of like we were just saying, the highest power of x dominates, a trillion squared, much bigger than 7 trillion. And so it doesn't matter that we're subtracting those other things. As x goes to infinity, this limit is equal to infinity. What work do you have to show? None. There's no work to show. It's very clear that this limit is equal to infinity. This one is a little bit trickier. If you tried multiplying the numerator and denominator by 1 over x squared, you could do that because you're always allowed to multiply by 1, and you get the limit as x approaches 1 of 1 plus 2 over x plus 1 over x squared, all over 3 plus 5 over x squared. But if you tried to say that that's equal to a third, you'd be completely wrong, because the limit as x approaches 1 of 2 over x is not equal to 0. It's equal to 2 over 1, or just 2. And so, whereas you could start this problem this way, it doesn't really make any sense to start this problem this way. Don't do that. This is just a straightforward limit. What is it equal to? Plug in 1. This is a rational function, perfectly well defined at x equals 1. You get 1 squared plus 2 plus 1, all over 3 times 1 squared plus 5. And what's that? That's a 4 in the numerator and an 8 in the denominator, so I think you get a half. And so don't get tricked by that. Only use this clever trick when we're taking limits as x approaches infinity or negative infinity. Okay, those were limits at infinity. Hope you enjoyed them. Have even more fun with the homework. See you soon.